Laboratories webinar. I'm Rick Trotta, Chair of the Federal Laboratory Consortium National Advisory Council. It's my pleasure to provide some introductory comments on the background leading up to this meeting, the objective of the webinar, how it will be conducted, and today's agenda. For the past 2 years, Dick Paul, Advisory Council Vice Chair, and I have been working with the Industrial Research Institute's External Technology Network on initiatives to build a stronger bridge between industry and the federal laboratory community. Expanding interaction with industry is one of the major tasks the FLC board asked the Advisory Council to be involved with. Collaboration with the Industrial Research Institute provides a great opportunity for the FLC and federal laboratories. IRI member companies account for approximately 2/3 of total U.S. industrial research, and these large companies have the resources to bring new technology to the marketplace. The FLC National Advisory Council has had a history of interaction with IRI. Chuck Larson, a longtime member of the National Advisory Council, was a former president of IRI, and Dick Paul was a past chair. This webinar replaces a panel session that would have taken place at the FLC National Meeting in Denver, which was canceled because of government travel restrictions caused by sequestration. Our plan for that meeting was a panel session in the morning, followed by an opportunity for one-on-one meetings in the afternoon with panelists and interested laboratory personnel to explore collaboration opportunities in more detail. We are following a similar format for this meeting, and there will be one-on-one sessions with each of the 5 panelists. The schedule will be displayed during the webinar and on the FLC website. The objective of this webinar is to provide a forum where industry can share specific technology needs with federal laboratories. We believe that understanding industry technology needs is an excellent place to start discussing collaboration. I want to thank all the presenters and especially Joe Fox, who worked to organize this webinar and will moderate the session. As you can see on the agenda, 5 major companies will share their specific technology needs. Ashland Performance Materials, Joe Fox, Director of Emerging and External Technologies. Dow Chemical, Gretchen Baier, Associate R&D Director of Government Programs. Weyerhaeuser, Miles Drake, Chief Technology Officer and Senior Vice President, Research. Monsanto, David Russell, Director of Technology Prospecting. And Goodyear Tire and Rubber, Derek Shuttleworth, Program Manager, External Science and Technology Programs. Their bios are posted on the FLC website, and their credentials are impressive. Approximately 25 other IRI ETN companies will participate as listeners. Each presenter has scheduled a follow-on webinar to answer questions, discuss needs in greater detail, and provide an opportunity for laboratories to discuss their capabilities and potential collaboration opportunities. Because of the busy agenda and time constraints, we will not be able to answer questions during this webinar. If you have any questions for our panelists, please enter them in the chat box in your webinar menu, which is located on the right side of the screen. The panelists will address these questions during their individual follow-on webinars in the coming weeks. You will be able to schedule a specific time slot during these individual webinars by contacting Michelle Chambers, who is organizing this webinar. Her email address is mchambers@totaltechnologyinc.net, which will be highlighted on the closing slides and posted on the website. In addition, if you have any questions for the presenters that you think of after the webinar, please send them to Michelle. Michelle asked me to mention the following. If you have any technical questions or issues during the webinar, type them in the chat box in your webinar menu for immediate assistance. The webinar will be recorded, and the recording and slides will be online within 1 week. You will receive an email about how to access the recording. At the conclusion of the webinar, there will be a brief survey, which I encourage you to complete. Your comments will help us in planning future webinars. Our federal laboratories are developing leading-edge technologies and are a great national resource. Linking these technical capabilities with industry is one way we can help bring new products to market and enhance U.S. competitiveness. Given the ever-increasing global competition, we need to leverage our federal laboratories now more than ever. We look forward to these webinars enhancing that process. And now I'm going to turn this over to Joe Fox, who will provide insight into the Industrial Research Institute's External Technology Network and introduce and moderate the session. I'll be watching our time schedule and back at the end for a brief wrap-up. Joe?
Thank you very much, Rick. And I am going to give an overview of the IRI's External Technology Network. IRI stands for the Industrial Research Institute, and it is celebrating its 75th anniversary this year. Consists of over 200 members, companies from industry, and federal laboratories. The mission of IRI is to enhance the effectiveness of technological innovation by networking the world's best practitioners and thought leaders to seek, share, learn, and create. IRI consists of 8 different networks ranging from new business development to human resources, and I'm going to focus on the External Technology Network, or ETN. The focus of ETN is on the sharing of best practices related to identification and acquisition of external technology. So the members are searching for technology outside of their own company. And for those of us who have been involved in technology and have been in many confidential discussions, the openness and willingness to share best practices at an ETN meeting is very refreshing. It is the largest network within the IRI, consisting of about 150 members, and I won't read you all the titles of the professionals involved, but it is people like managers of technology transfer, external research directors, and technology scouts. The ETN consists of both industrial members and representatives from the federal laboratories. From industry, you have chemical companies represented like Air Products, Ashland, DuPont, Eastman Chemical, and Lord Corporation. You have materials companies, you have consumer products companies like Kimberly-Clark, SC Johnson, and Sherwin-Williams, and you also have representatives from many of the federal laboratories and the National Science Foundation. Some examples of discussion topics at ETN meetings are interactions with universities, federal laboratories, and small companies, budgeting for external technology, the creation and distribution of external technology needs lists, very relevant to today's discussion, using open innovation intermediaries to find technology, and organizational structures for external technology. Here's the agenda of a recent meeting. Some other topics include corporate venture capital and technology scouting. A typical ETN meeting usually brings together 20 to 40 representatives from industry and the federal laboratories for typically a 1.5-day meeting. There is an opening roundtable where each member of the network gets to share issues and hot topics relevant to their company. And then the remainder of the agenda consists of presentations and panel discussions by member companies, and I've given an example here where you've got selection criteria for university and national lab partners with 3 industry members and Tony Buckenfusco from the University Industry Demonstration Program. We also invite in external speakers, and here's an example very relevant today. A couple of years ago, Karina Edmonds, the Technology Transfer Coordinator from the US DOE, spoke at an ETN meeting. And then it is followed by a group dinner and gift exchange, and a lot of friendships have resulted from ETN meetings over the years. The benefits of being a member of ETN: it's an excellent source of best practices, especially for people new to an external technology role. I became a member of ETN in 2006, and it is fair to say that nearly everything that I have done with respect to external technology here at Ashland has its roots in ETN. It also provides an opportunity for excellent networking opportunities. Ashland has had several collaborative relationships developed through conversations at ETN meetings. For more information about ETN, you can contact any of the current ETN co-chairs. Linda Belts from Weyerhaeuser is actually one of those co-chairs, also Tom Mildenhall from KimberlyClark, and Mike Cameron from Sherwin-Williams. I am a former co-chair of the network, and I also will welcome any contact or questions that anyone may have. At this time, I think I'm going to turn it over to Gretchen Baier.
Thanks, Joe, and thank you, Rick, as well, for hosting us. I'm very much looking forward to this session. Hopefully, you can see my slides. Just now putting them in slide view. So I'm going to talk about research areas of interest for the Dow Chemical Company. First, just a word about Dow for those of you who might not be familiar with Dow. It was founded by H.H. Dow. Our headquarters are in Midland, Michigan. We are the largest U.S. chemical company. We have 52,000 employees worldwide, more than 5,000 products, 197 sites in 36 countries, customers in over 160 countries. So you can see we have a very large and global footprint. And our sales last year were $57 billion. So this puts Dow as a Fortune 50 company. And in the overall scheme of things, basically as a chemical company, we take feedstocks plus energy and convert that to chemicals and materials. Dow's operating segments, since we are a large company, it's a little bit difficult to really give a one-slide overview of our company. But here's an attempt at that. We're divided into 5 divisions: advanced materials, agricultural sciences, performance materials, performance plastics, and feedstocks and energy. And within those groups, you can see just a wide variety of business areas. I'm not going to read through these, but I will hold this up here for just a minute for you to take a glance. I think it's easiest to describe Dow as things that we don't do. And basically, we are not in pharma. And we also are mostly organic chemicals, so very little in the inorganic space, you know, metals and things like that. I'd like to reference you down to the website below at www.dow.com. Under the Investors tab, there's a Dow at a glance. There's a data book that it's not. In addition, there is obviously our financial statements for the you know, the 10Ks and things like that, annual reports. But the data book is actually another resource that I think you would find very interesting and goes into these different areas in a little bit more detail in how they're divided up for the market segments and some of the key highlights for the last year as well. So we have a large research and development organization. I'm actually part of R&D. Our annual budget is about $1.7 billion. That's globally. We have about 5,500 researchers worldwide. Most of them are PhDs. And our research and development runs the gamut from product research and product process research to application development, obviously to commercialization. Typical of industry, we don't really do that much basic research, and that's really where we rely on our external partners to collaborate on these type of activities with universities and federal labs and research institutes as well. So Dow has a very long and rich history with the federal labs. We have many long-standing relationships. I can rattle off a bunch of them and success stories. A lot of these relationships have stemmed out of user agreements, and that includes both proprietary and non-proprietary. We find that you know, it's an excellent basis to have a presence, you know, at a federal lab and really develop those relationships that then can become deeper and more collaborative. And these often have stemmed into we have experienced the full gamut of agreement types: work for others, creatives, grants, material transfers. We're part of several hubs. Very interested in the EFRC, the Department of Energy, and others as well. So, we feel very, very thrilled to have had these various experiences. And also looking back, we really touch most of the U.S. agencies as well: Department of Energy, Department of Defense, Department of Commerce, Department of Interior, USDA. We've also worked some with NIH. I don't know why this keeps on coming up. I hope you don't see it. As well. And so we also, look forward to, continuing to deepen those relationships. So my specific role, I mentioned earlier that I am in research and development, and I'm in Dow's external technology group, and I'm really interested in helping our Dow researchers identify and set up collaborations with external partners. This is mostly in the R&D space, but not limited to the R&D space. In my list of agencies, I neglected to mention the Department of Homeland Security, for instance. That's also an area of interest for us. As far as that goes, I'm really mostly about collaborations. We have a separate but parallel group that's interested in licensing or tech scouting, and we also have a venture capital group. And so clearly any overlaps or interests here out of this presentation, I'd be more than happy to discuss those with you and make the appropriate connections with those other groups as well. So the next slide is I'm going to jump into now. Well, this is really a summary of the slides I'm going to present in a little bit more detail. I've divided this session into two segments. One is strategic areas, and then number two is long-term technologies. It's really, really difficult for a large chemical company to, give some sort of picture at the right level of detail on what our interest areas are or our needs are. So I'm sure looking through this, list, it seems very high level, but I think that these are topics that I would be interested in learning more about expertise areas and collaborative ideas for the strategic areas. For the long-term technologies, these, as I go into these in a little bit more detail, it would be tempting to call this holy grails, and so I don't want that term to be frightening, but that's from the industrial perspective, and these longer-term technologies really are things that we are interested in, and these could lead to major breakthroughs as well for us. And these are in another level of detail. Now, what is missing from my presentation here is what I would say is what's the immediate technology needs that we have. And I'm going to have to apologize for that up front, but that would never make it through our external release process for reasons I'm sure everybody could understand. And that's why it's important to have these initial discussions, or at least high-level ones. Then as we do hone in on an area, obviously that we can, execute the appropriate NDAs and things like that for maybe the shorter-term opportunities. Going into the strategic opportunities, again, the list is the same as before, just with another level of detail. Agricultural, novel crop protection chemicals, elite plant genetics, biotechnology traits, various enabling technologies such as controlled release and things like that. We're very interested in functional foods, so seeds for healthy oils, for instance, quality traits, ruminant nutrition, electronics and communications. These are some of the areas that we have active projects in: photoresist, interconnect, circuit boards, displays, and lighting. That would include, obviously solid-state lighting. I think I, would be of particular interest in talking to U.S. federal labs about this, since we do see a lot of offshoring of those technology areas. Packaging and converting. So here it is not electronics packaging. It's really food packaging and the plastic films that you use on a daily basis, probably. And so packaging solutions that can be, sealing, it can be barrier properties, new package designs. Photovoltaic films, for instance, as well would fall into this, and post-harvest freshness. So this is where, would get at multifunctional packaging. Alternative energy and feedstocks. The chemical industry is the largest industrial sector for using energy because it's both a feedstock for us and it requires energy to make chemicals. So this is a very important topic to us. So always looking for renewable and sustainable resources. Wind energy is interesting, both for energy, but materials go into making the wind blades, epoxies, and composites. Energy storage here is very broadly defined. It includes batteries. Heat transfer fluids. We're the largest producer of fluids for concentrating solar power, electrical and telecommunications. Energy production and efficiency is very interesting, both for our products but for our internal use as well. Here are some examples. Insulation. Styrofoam is one of our brand names. Photovoltaics. Again, we have a product around there. Separation science is a very important area for us, both in water separations, which is a business area, but also process separations because we do just a lot of those in our own capacity. Home and personal care, cleaning, biodegradable surfactants, paper and publishing, construction, green building materials, smart windows, adhesives, construction chemicals, paints and coatings. We do a lot of latexes, for instance, polyurethanes, transportation. So again, you can see how this list gets a little overwhelming after a while. But I would, these slides will be available afterwards. For the long-term technology areas, you're going to see a little bit more detail on these. There are two slides here on solar. Again, we readily admit that these are very challenging and long-term goals, but they are really technology areas that are of great interest to us. So I'll just, instead of reading through these, I'll give just a second for people to read this. And then solar number 2. And we do have existing collaborations going on with several universities and the Department of Energy on this topic. The others aren't quite so lengthy, but direct activation of alkanes to products, so with high carbon efficiency, high conversion. I'd like to make sure that it's interesting transitioning from solar to a more traditional chemical process, but we do find that there is less attention on these more traditional technology areas, and we would really like to see more emphasis in these. So that's where the remainder of my slides really are. So here's some more around catalysis, cross-coupling. And then we've got some more catalysts here. This is on low-pressure polyolefin catalysts. And so it's really incorporating polar monomers with ethylene. We've got high-strength composites, right? So high-strength to low weight. And, of course, low cost is always interesting as well. But epoxies and urethane thermosets are very important to us and compatible with that. Low-cost, high-modulus, high-strength fibers as well. We are interested in 3D printing and materials for that. Non-halogen flame retardant materials without a trade-off in performance. I think the without trade-off in performance is true for all of these topic areas. Isocyanate-free foams and adhesives as well. And along with this, it's not included in the slides, would be formaldehyde-free products too. There are some basic chemical intermediates that we just haven't found a good alternative for. Non-epichlorohydrin routes to liquid epoxy resins. And then for the last slide here, general areas that specifically wanted to call out. I had mentioned earlier the importance of separations for us. advanced low-energy separations. Really, you can't emphasize that one enough. Economical recovery of low-waste heat, nitrogen fixation, oxygen transport at low temperature, and hydrogen transport membranes that are capable of operating at high fluxes and high temperatures. So with that, that really ends what I wanted to review with the group, and I really would like to thank you for your attention. Thank you. And with that, I think it's being turned over to Miles Drake.
Hi, this is Miles Drake. Can you see the presentation?
Yes.
Okay, good. Well, hi, I'm Miles Drake. I'm standing in for Linda Beltz, who's our Director of Technology Partnerships, and you saw that she's highly engaged with the ETN network. She unfortunately had to run off somewhere else in the world today. But what I'd like to do is, it'll be a slightly different tack from what you saw from Dow, because we're obviously a much smaller in terms of our research resource. Although I'd like to make a comment that Weyerhaeuser is sort of unique, certainly in North America, in having a long-term R&D capability that's allowed us to do some very innovative and interesting things over time, and we really are a good opportunity to receive technology and convert it into value. But what I'd like to sort of highlight right up front is, I mean, on the line there'll be people from the USDA or the Forest Products Labs who will know everything that I'm going to say. But I think it's my experience that a lot of people don't really understand the sort of scale and dimension of wood as this enormous worldwide sustainable resource, which is very flexible in what you can make of it. And long term, as we move to a more sustainable world in the future, I believe that the fact that you've got this scale resource, which the volume of wood harvested in the world is comparable, it's a little less than, but comparable to the volume of oil that's extracted. It's coming in a sustainable way from non-food land. So I think there's going to be enormous opportunities long term to create more and more products from wood. And I'd like to just touch on some of the things that we have an interest in, and some will be near term and some might be longer term. So our company, our vision is around superior sustainable solutions for the world. And if you look at the little icon on the right, it's how we see ourselves, which is owners of large-scale, landscape-scale land and forest. So we have 6 million acres of forest in the U.S. and access to about 20 million acres of crown lands in Canada. And then we've got some holdings in South America as well. And we see this as a resource that the next circle around that sort of illustrates the variety of things that we're creating value of from the land and forest. Now we're organized, if you look at the top few bullets on the left, we're organized into 4 businesses. Timberland, which is focused on sustainable scale production of timber and biomass. Wood Products, which converts timber into lumber and engineered products. That's, for example, you see as homes are going up, you can see the cladding made of the board, which oriented strand board, which is produced from flakes of wood glued together again by adhesives, and a whole set of other structural members made from essentially either glued sheets of wood, laminated wood, or fiber. We've got a home building business, which is a series of regional builders who we got 4 or 5 regional home builders. And then our cellulose fibers business, which takes wood and separates it essentially into cellulose fluff and produces products that are used in a whole variety of applications, from hygiene, tissue and towel, through to things like we're using fluff products as additives, and I'll talk a little bit about that later. And then we've got three, if you like, emerging businesses or major initiatives: Weyerhaeuser Solutions, where we're bringing forest-based solutions to industrial clients of all sorts, using the skill and knowledge we have around managing forests and converting forest resources into products as a service, for example, to companies that might want to do something around their greening their energy supply and finding ways to get a continuous supply of wood-based products to do that. And then Catchlight Energy, we have a joint venture with Chevron looking at liquid transportation fuels from forest feedstocks. And that's been an ongoing JV where we're looking at how to take forest resources, how to do it sustainably at scale and at cost to convert through to liquid transportation fuels. If I look at the what are our big drivers for technical innovation that will bring us value and therefore create some interest, and we are a large scale, a number of our supply chains are really commodity supply chains, and we have some differentiated ones, but under the rubric of sort of supply chain cost reduction, there's everything from seed to timber, getting to very efficient, what we call precision landscape forestry, which is being able to generate wood at quality wood at scale at the lowest possible cost. And if you can imagine that once you've planted a seedling, it might be 30 years before you harvest the wood. Any costs that are incurred early on, if you look at the NPV of those, they escalate rapidly. So things have to be done extraordinarily efficiently there. In pulp and paper processing, that's everything from control systems, improved feedstock costs, and reusing sort of byproducts for energy production and other things. In lumber and engineered wood manufacturing technology, there's a whole host of technologies associated, even with something as simple as generating 2x4s, and I'll touch on that. And then we're being driven by, as I said at the start, wood is a very large-scale sustainable resource, and there are some long-range drivers which we think are going to be important to drive innovation in this area. Affordable green building, that's dwellings for there's going to have to be something like 2 billion dwellings by 2040 created in the world, and wood is a way to create a dwelling in a sustainable feedstock that has sequesters carbon essentially in the building. The rising global demand for hygiene and natural textiles. So as people emerge into the middle class, one of the first things people do with some disposable income is to put diapers on their babies and to have hygiene products. So that's driving global growth in the use of cellulose materials for that. Really taken around the world by companies like P&G and KimberlyClark. And then the use of natural textiles, particularly long-term. Cotton has some challenges around water use. Quarter of the world's pesticides are used to sustain cotton. So displacing cotton with alternative natural textiles is something that is likely to happen long-term. And then I mentioned the sustainable fuels for power and transportation from forest resources. And then finally, emerging long-term will be carbon and eco-footprint reduction using forest resources and gaining value for the ecosystem services like clean water. So those are some of our cost and market drivers. And if you don't need to, I'm not going to go through this slide, but just you can. Linda created this, and it's on our website. You can go to weyerhaeuser.com you can find this sort of summary of all of the areas. But really today I just wanted to focus on a few things which, again, there's a lot of people who are collaborating with USDA, Forest Products Labs, and the DOE and some other of the institutions. But I want to sort of see if I can trawl for the unexpected in this dialogue, and I look forward to hearing some things that we won't know about or won't have thought about. So in forestry, as I mentioned, the critical driver is getting the whole supply chain very efficient. And one of the big issues for any forest company is safe, low-cost inventory of forest at landscape scale. And what that means is understanding where the trees are exactly, what volume there is, ideally what quality of wood you have in the trees, issues around are there patches that are engaged in having some stresses, and there's health issues which could be anything from insects to water stress, or even lack of the right nutrients, and then also the local growth rate. Because if you know all this, you can both ensure that everything is working well in your forest, and also you can plan when and where to harvest efficiently for the lowest cost supply chain. So low-cost inventory, and the sort of things that are done here are using Landsat, using LiDAR techniques to start to see where trees are and how high they are and how they're growing. And there's around that, there's some other technologies that are both crunching big data to understand large-scale images and get information out of them, and alternative sensing methods for getting at these challenges. One thing which is, if you think of the Northwest where our headquarters are located, we're planting Douglas fir trees on very steep and rugged terrain, and this is done by hand by migrant labor or students. And there is, in general, a need to find ways to plant seedlings in rugged conditions, which at the moment humans are the only thing that can do this, and ideas around how that might be done differently, it would be of interest. And then another challenge which we have is measurement of carbon storage and fluxes in forest environments at scale. So in other words, in the future, how will we know what the carbon exchange and flux is in the forest, and that's coming out of the soil and into the air? How do you measure that CO2 flux? And it's a very challenging problem. You can put little devices and cap them and have very sophisticated systems, but they tend to be very high cost. And if you want to measure over acres of land and get some idea over acres of land, it gets very expensive to do. And we'd like ideas on how you can measure CO2 flux and also measure soil carbon and soil carbon changes over time. If we go to the wood processing, which is now the next stage, I talked about the forestry. Now you take wood and you chop it up into 2x4s and timber. Then one big issue is wood is a wonderful construction material, but of course, being a natural material, it does have some drawbacks around in terms of its environmental performance, if you like, in terms of resistance to a number of things. And we really have a mantra of we want to improve performance against fire. So what can we do to reduce the combustibility? Water, which is both from dimensional changes and making it susceptible to mold and other things. Bugs, which is the both mold and insects. Energy, ideas for how we can construct homes primarily of wood with better energy performance, and then ease of use. And that means how do you make it easier to use wood to construct homes and industrial buildings. And then obviously when it comes to the wood, I talked about engineered wood, which is glued together pieces of wood, either laminated beams through to chips of wood stuck together. The adhesives are really critical for this, and at large scale they need to be low cost and high performance against those issues of fire, water, bugs, and energy that I mentioned above. One of the other things about wood is it is, as a natural material, it is variable, and every log is a bit different, and every piece of wood you cut out of a log is a bit different, and our goal is to make everything very reproducible and consistent. And we've over decades, we've developed a number of very valuable high-rate, non-destructive evaluation of wood. And for example, we actually do acoustic measurements on enough 2x4s to circle the world every month in terms of the length of wood that we're testing. And we need high-rate, rugged evaluation of both logs and of lumber and timber, so that we can look at things like strength, modulus, moisture content, internal structure and defects. And there's, related to that would be, I mean, one way that is used is acoustic measurements, so you can tap wood and listen to the frequencies generated, or you can measure the velocity of sound in it, which gives you some go-bys of some of these measures. But then how can you, at a very high rate, so that if you tap a piece of wood, analyze the complex spectrum of acoustics that come out of that, and then look at and get some more information about the what's going on in a piece of wood. So it has to be done at high speed, it's got to be rugged, and it has to really, the key things to get at are internal defects, strength, modulus, and moisture. Finally, in cellulose fibers, we're looking at use of cellulose in a lot of applications, many of which are in composites. And I've put up on here the example of our product called Thrive, which Ford has been collaborating with us. And it's putting cellulose into polypropylene to make a lighter weight, easy to process, partially greener material that you can now have, you can stiffen it, you can lightweight it, and actually take cost out and improve processing by putting cellulose into polypropylene. And we're interested in modeling and characterization of sort of natural materials into composites of all sorts, including polymers, cement, concrete. There's some big issues around replacing asbestos in many countries now that are still using it. And finally, modeling of multi-phase slurries. That would be pulp slurries under high shear for looking at mechanical effects. So our follow-up session is June the 25th, and this tells you how to sign it up. And just Linda's put on here, we're proud of the fact that Weyerhaeuser is recognized in many ways for its corporate and product sustainability and ethics, and that we think that, as I've said, long term, if we're going to operate as a provider of sustainable solutions, we've got to have a sustainable and ethical company. So I think I'll stop there. That's a quick overview and just a teaser of some of the things I think we'd be interested in. Thanks.
Okay.
Thank you.
And I'm taking over now. This is Joe Fox from Ashland. And I'm going to begin with a brief overview of Ashland. We are a global diversified specialty chemical company with about $8 billion in sales. We are no longer Ashland Oil. We were for about 75 years, but 7 years ago we divested our marketing and refining assets to Marathon Oil and have focused since then on specialty chemicals. Towards that end, we have been strengthened by two recent acquisitions, Hercules in 2008 and International Specialty Products in 2011. So right now we consist of four divisions: Consumer Markets, which really equates to Valvoline. Our Water Technologies division provides water treatment chemicals for the pulp and paper industry and for industrial water treatment. Our Specialty Ingredients division sells functional additives into a wide variety of industries, cosmetics, pharmaceuticals, food, things for rheology control. And our Performance Materials division, which sells resins for adhesives and composites. And that is the division that I represent, and I will be focusing on the external technology needs of Performance Materials. So I'll tell you a little bit more about that division. Our primary market focus is in transportation, building and construction, and packaging and converting. We are business to business. Our major product lines are resins for composites, like the resins that would be used in this truck hood or in this kitchen countertop. We also sell a wide variety of high-performance adhesives, structural adhesives for bonding composites, for bonding wood, pressure-sensitive adhesives like the one that is holding this decal on the bus, or flexible packaging adhesives for the food packaging industry. Almost all of our products are based on thermoset resin chemistry. We do very little with thermoplastics. Unsaturated polyesters and vinyl esters are our workhorse resins for composites. The urethanes are primarily used for our structural adhesives. The acrylics are the workhorse raw materials for our pressure-sensitive adhesives. And then we also have hybrid systems. So I'm going to talk about these 6 needs today. In the interest of time, I'm not going to read them to you, but I will go through them in this order, and they span both our composites and our adhesives businesses. So let's begin with bio-based chemical building blocks for thermoset resins, and we have an interest in bio-based chemicals for both composites and adhesives. Our motivation is really Ashland wants to reduce our dependence on petroleum, and we are looking for lower cost raw materials with greater price stability and greater accessibility relative to petroleum. A second motivation is pull from our customers for green, sustainable products. And a good example of that are Envirez unsaturated polyester resins. About a decade ago, John Deere was looking to create products for farmers with crops grown by farmers. And we used bio-based materials to create the resins that are used in the panels on these tractors and combines. We continue to be very active in this area, and we have 2 needs: cost-effective sources of sugar for chemical production from biomass, and also highly selective organisms or catalysts for the production of chemicals. And I'll use this flow chart here to describe that need in a little bit more detail. Here I'm showing the vision for chemical production at an ethanol biorefinery. And primarily that biorefinery is taking biomass and converting it to fuel. Our vision is to also have that biorefinery produce chemicals, like a petroleum refinery, go through a sugar solution, and then either biologically or catalytically selectively convert those sugars into the monomeric building blocks that we use to make resins like those Envirez resins. Ashland does not intend to build or operate a biorefinery, but we do represent a strong downstream channel-to-market partner for bio-based chemicals. So we are looking for upstream partners that either have the hardware or the software for these conversions. By hardware, I mean things like fermentation tanks, biomass handling equipment, or distillation equipment. By software, I mean the organisms or the catalysts that can do these conversions very selectively. Also, to make this entire scheme cost-effective, it's very important that you have a cost-effective feedstock and a cost-effective sugar solution. So we are interested in sugar solutions that are between 10 to 12 cents a pound on a dry basis. Specific chemicals that we're interested in from a biorefinery. We are interested in short-chain glycols and short-chain unsaturated diacids. Those are the workhorse building blocks for our unsaturated polyester resins. We are interested in low glass transition temperature acrylates, like butyl acrylate and 2-ethyl hexylacrylate, which comprise our pressure-sensitive adhesives. We also have interest in aromatic molecules, like isophthalic acid, terephthalic acid, and replacements for bisphenol A. In terms of economics, these chemicals from biomass must be cost competitive with their petroleum-based equivalents. And as I've mentioned, we are a chemistry company. We are not a microbiology company, so we are looking for technology, enzymes, organisms for the selective conversion of biomass to these chemicals. Our second need are for thermoset resins with improved fire resistance. And I've already shown you that composites are used in the transportation and building and construction industry. I showed you that truck hood and that countertop. Well, we would like to expand the use of thermoset composites into the building and construction industry, structural and non-structural building components. Also in the transportation industry, there are opportunities for high-speed rail and on cruise ships for composites with improved fire resistance. So what we are looking for are thermoset resins with lower flame spread, smoke generation, and smoke toxicity. Improved fire-resistant performance. At the same time, not compromising the processability that is necessary for composite fabrication of methods like infusion and pultrusion, and also not compromising the mechanical properties that you obtain in these composites when you reinforce them with glass fibers. A little bit more about this need. The resins do need to meet the requirements for mass transit, architectural, and maritime applications. I've listed some of the specific tests there. This is an example of an NFPA 285 test. So, types of technology we're interested in. We're interested in resin technology and additive technology. Resins that, built into the structure, there is inherently better fire resistance. Or additives that can be incorporated into the liquid resin without large increases in viscosity, which would compromise processability. Like Dow, we also have an interest in halogen-free systems. Types of technology we are not interested in. I mentioned that we are a thermoset resin company, so we're really not interested in thermoplastics. We're also not interested in post-cure solutions like intumescent coatings. Moving on to the third need. We are interested in thermoset resins with improved weatherability. And our motivation here is to expand the ability of thermoset composites to be used in outdoor applications, like the facade in this building or the panels in this skylight. So we are looking here for resin systems with greater resistance to UV, resins that demonstrate improved QUV and xenon arc performance. We're also interested in resins that have greater resistance to moisture and improved freeze-thaw behavior. On a microstructural level, some of these improvements really translate into having a more stable interface between the resin and the fibers and the aggregate that comprise the composite. Again, like the previous need, we are not interested in coatings that are applied post-cure. We'd like this to be built in to the resin system. Staying on the composites theme, composite materials for green building. Here, Ashland is trying to take advantage of the benefits of composites to increase their utilization in the building and construction industry, especially in green buildings. And some of the benefits that I mean here are things like energy efficiency. Composites are very insulating relative to metals. Durability. Composites are very durable relative to things like concrete and wood. They can be easy to install. They're lightweight relative to concrete and metals. They have very good corrosion resistance, and they can have very attractive aesthetics, which is very good for architectural applications. So what we're looking for here are really prototypes. Prototypes where composites can replace or enhance traditional materials of construction, like concrete, steel, aluminum, and wood. So just a little bit more about the types of materials or prototypes that we're interested in. We're very interested in hybrid materials, where composites are used with wood, with concrete, or with foam to give new materials, new hybrid materials. We're interested in composites with extremely high R values so that they could be used in window and door frames or in curtain wall frames. We're interested in low density composites again, from an insulation standpoint, but also in terms of ease of installation. And we're interested in composites with unique aesthetics. I've shown here, for example, a composite that is going to be used as a rain screen on the new San Francisco Museum of Modern Art. Since we're interested in dissimilar materials, we're also interested in joining technology for dissimilar materials. One more for composites, we're also interested in recycling technology for thermoset composites. Why are we interested in recycling? Because our customers are interested in recycling. And what we're trying to do here is to provide resin and composite users who are concerned about the total life cycle of their products with viable options for recycling or reuse. We'd really like to give them options other than a landfill. So the need here is for economically attractive technologies for the recycling or reuse of thermoset composites or thermoset resins. Again, we are not interested in thermoplastics. We have a tougher nut to crack here with thermosets. So technologies of interest would be reversible thermosetting resins, efficient dissolution or digestion processes, and I'll just give an example here. Ashland currently can use post-consumer PET, which we can digest and then obtain the raw materials that we can use to make unsaturated polyester resins. We're also interested in novel or improved shredding or post-shredding technology, which would enable thermoset composites to be used as a filler or in other applications. I'm going to finish up one more need, and this one is on the adhesive side. We are interested in low migration adhesives and coatings for food packaging. Our motivation is that more and more products are using flexible packaging, like the ones that you see in the freezer section at your grocery store, and also that the expectations of brand owners for safe packaging materials are constantly increasing. So we are very interested in laminating adhesives and coatings comprised of thermosetting resins with a low propensity to migrate through the packaging films into the food. And here's a very simple package over here where you've got two films of polypropylene. The first film is reverse printed with an ink, and then you have a laminating adhesive bonding this all together. We are interested in adhesives whose components will not migrate through that white film of polypropylene into the food. So we're interested in resins with low residual monomer content, fast curing adhesives, which again will reduce the amount of low molecular weight constituents in your adhesive. We're also interested in photoinitiator-free and solvent-free adhesives. Not only are we interested in chemistry, we're also interested in supporting technology. We're interested in model software that enables you to model migration through these packages. And on the analytical front, we're interested in high-throughput, ultra-low detection analytical methods for migration testing. These methods can take a lot of time, and the limits that you need to detect are constantly going down. So that really finishes up my presentation. My follow-up session is Thursday, June the 27th. Again, you can register with Michelle to help her put together a schedule. Please indicate the technology need or needs you would like to discuss and how much time you think we will need for an initial discussion. So with this, I think I will turn it over to Dave, and I'd like to thank you for your attention.
Are you able to see my screen?
Yes, we can see it.
Oh, okay, great. Let me just. So what I'd like to do, first I'd like to thank the organizers and the labs for a chance to tell you a bit about Monsanto. I'm going to give you a brief overview of where Monsanto is today to set up some of the very specific technologies that I'd like to focus on. So Monsanto 10 and 15 years ago was a chemical company that was becoming a seeds and traits company. We were starting to work more and more in different aspects of agriculture. Today we are really, most of our
sales is really based on seeds and traits, and we're really a seed company that happens to have a small amount of chemistry going on as well. We are global with our headquarters in the U.S. Most of our basic research is in the U.S., both in St. Louis and as well as a number of different labs scattered from coast to coast. We also have research labs in India, China, and Brazil. On the breeding side, we have breeding stations listed all across the world. We're about 20,000 employees, and this last year we will have spent about $1.4 billion on R&D. So we do invest pretty seriously in R&D. So I indicated we're not really a chemical company anymore. The one area in egg productivity where we are still very active is we still do make glyphosate, which is the active in Roundup. So that is one piece of chemistry, but most of our work is really in what we call seeds and traits, which is where we bring in plant biotechnology, genomics, and other aspects. And I'll talk a bit more about those. Our main products that go out to the growers were in row crops: corn, soybean, cotton, canola. Most recently, we've added wheat and sugarcane a few years back. About 5 to 8 years ago, we added a couple of different vegetable seed companies, and now we're a very large vegetable seed player as well in providing different vegetables to commercial growers. So I want to move right into the technology, and I'm specifically going to focus on some of the things that you might not normally think of a seed company being interested in. I think that everybody understands that a company like Monsanto, who is known for their genetically modified crops, does a lot of work around plant biology and plant biotechnology. We also, though, are very active in breeding. I'll talk a bit about some of our specific needs in advanced breeding technologies, some in biotechnology. A third area is what we call biologicals. These are really agricultural-related microbes and plant microbe interactions. And this is an area that I'll show you some very specific needs that we have in that area, which is a fairly new one for us. On the chemistry side, while we don't do a lot of our own chemistry discovery anymore, we are very active in being able to use different chemistries that might help the performance of some of our different products, particularly seeds and seed treatments. And then finally, I'll talk a bit about agronomics, and this is our catch-all for all the different tools that can be brought to bear to help the grower, the farmer, really understand how to best use his land, his water, fertilizer, his seed to get the most per acre. Our view and the thing that's driving us forward is that we need to produce more while using less. And so we are looking at tools that will help the farmer make those sorts of decisions. And I'll talk a bit about that towards the end, some specific examples. Okay. This is a slide of a lot of different areas at fairly high level that we're interested in. I'm only going to focus on a few of these in the following slides, but I wanted to remind you that we do have on the Monsanto.com website, you can go to partnering, and you'll find a section that has more detail on a list like this, as well as different ways that you can get a hold of people inside of Monsanto should you have something that you want to follow up with on us. And all those different connections actually go through our team to try and sort out who are the right people at Monsanto who might be interested in your ideas. I'm going to focus on some specifics around plant breeding, detection techniques, particularly out in the field, precision agriculture, sensing, particularly remote sensing, automation, and of course we have a lot of needs on the computational side to pull all these pieces together. So the first area I'd like to focus on is around breeding, and we spend a lot of time on developing new technologies that will help us speed up breeding, help us get make better decisions when we are doing our crosses and trying to advance germplasm. And so as part of this, we've done a lot of work in genotyping, and we probably do more genotyping than just about anybody else out there. This last year, we'll have done hundreds of millions of genotype marker data points. So we're a very large player on the genotyping. We have automated some of those processes so that we can take materials directly from a seed, extract the DNA, do the marker analysis, pull that data, and try and compare it to the phenotype data that you to help us drive faster decisions so we can make more rapid and better advancement decisions on our breeding choices. So we're very interested in any technologies that can help us further increase our throughput, reduce cost, of course, and to provide very rapid analysis of the data so that we can pull things together. So all of these, and I'll come back a bit more to the phenotyping in a later slide, but all aspects of genotyping, be it from seed or from leaf, we have a great interest in. On the pipeline, our technology pipeline in terms of how we produce and create new events, we have a number of areas where we're quite active, and certainly areas where we are always looking for new ideas. One area specifically, RNAi technology. We have a new product that will be coming out that specifically uses RNAi that's expressed inside of a plant. We are now looking, we have examples now where we can actually use the RNAi topically to create changes in the plants, or certainly changes in how insects, diseases, viruses that might be attacking the plant. And so RNAi technology, particularly RNAi delivery technologies out in the field, are of great interest to us, and we're certainly would love to talk about any of those ideas. We do a lot of work around automation, and we're constantly looking for improved automation, and particularly the imaging and phenotyping that comes with that automation, so we can gather plant phenotypes more rapidly, both in the greenhouse and in the next slide you'll see out in the field. This is of interest. I've already talked about the fact that we do a lot of genotyping. It's very useful if we can now tie other markers to all those genetic markers, such as metabolites or proteins. And so any kind of proteomic or metabolomic high throughput systems are of great interest to us. Again, could be in leaf or in seed, depending on the specific examples. Okay. Now I wanted to switch over to an area that probably hasn't got as much attention in the past as it deserves, and that is really tools that help us understand what is going on in the field. And I'll kind of do this from large to small. Certainly remote sensing is very important to us to understand, both in our research plots as well as in commercial plots. What's happening in the fields, what's happening on the soil, how do we map the behavior that's going on, and is there anything going on? So remote sensing, from satellite to your Cessna to a drone that's carrying imaging equipment. We're very interested in people who have improved technologies in those areas. Down on the surface, in-field robotics are of great interest. If you had an affordable Mars rover, that would be ideal, but we need some way to be able to send equipment down the field to do sampling, to do imaging, to identify specific plants in the field. And so in-field robotics, this is a largely untapped field for most people. We'd be very interested in people who are working in that area. A layer down is soil and environmental sensors, and this is really to understand what's going on in the soil underneath going down, several feet in the soil in terms of nutrients, water holding, and so forth. These sorts of sensors are of great interest to us. Plant health itself, and again, being able to do it remotely to look at what is going on with specific plants in the field during the season so that you don't have to send people out with clipboards. You can actually do this all in an automated fashion. And then finally, for the field is what we call POC, field diagnostics. And this is a point of care, if you will, for those people who are working on what they believe is let's say a DNA or protein detection system for use in the clinic. We have the exact same need in the field. And this is for the breeders to be able to walk the fields looking at their genotyping and phenotyping information, be able to tie them together. And so we want to be able to do rapid DNA or protein analysis. And by rapid, I'm talking 5, 10, 15 minutes, not 2 to 3 hour thermal cycling sort of reaction that's typically used. And so we're very interested in people who might have ideas on how to do very rapid nucleic acid or protein detection. Finally, just 2 last areas that are new for us in the last couple of years. One is called ag biologicals and the other integrated farming. On the ag biologicals, I've already talked about one example of this, the RNAi that can be applied topically, both to affect how the plant behaves as well as things as insects, virus, weeds, and so forth. The other is around microbes and plant microbe interactions, and this is an area that's gained a lot of attention in the last year or so in agriculture, and it's an area that we're very interested in as well in terms of people who have a good understanding of what's going on, particularly what's going on with root systems and root imaging and understanding of root interactions. And then the final slide is really around integrated farming solutions. And this is actually our commercial product that we'll have coming out. This next year, in fact, it will be launched. But the idea here is to really provide better information to the grower, to the farmer who's has limited, his most limited resource is actually the land that he has. And so he wants to get the most out of it. We're trying to find out how we can gather more data to give him better, a better prescription. We call them field scripts, so that they can use this to manage their crop both at planting and through this season. And so this ties in a lot of the different aspects that I've talked about in terms of data types, such as remote sensing, soil mapping, understanding the germplasm and genetics that we're able to provide the farmer, and then having the predictive analysis by pulling all these different types of data sets together to give them the best chance of getting the most out of their crop in their season. So that's what we call integrated farming solutions. So I think that's where I'll stop. Our follow-up session is on the 26th, and as before, if you contact Michelle, tell her what it is that you would like to talk about and how much time you think we might need. We would love a chance to talk with you. Thank you.
Hello, this is Derek Shuttleworth from Goodyear in Akron. I hope you can see my screen. If anybody can't, then please speak up. Thank you for the opportunity, Joe and Rick, for putting this together. This is a wonderful opportunity to share some of our technology challenges with such a large and widely skilled audience. A lot like many of the others, I'm going to go over a little bit of background about our company. And a little more so than what you've heard so far, I'll be talking more about our product, that being tires, because we manufacture just about one product. And that, I think, will give you some insight from the technical standpoint of how our needs are being derived, the needs I'll talk to you about, how they're being derived from the way the modern tire is constructed and the way it's expected to function. In terms of contact with the lads so far, We've had occasional contact with many of the people on the line, but chief among those is, of course, I should acknowledge Sandia. We've had a long relationship for several decades with Sandia. So, oops, try and make this go forward. Excuse me. My contact information is right there, by the way. Just about Goodyear, one of the world's most recognized brands. We manufacture tires for almost every kind of vehicle. Notably on there, I want to mention that we have manufacturing using 27,000 people in North America still, and 16,000 of those are manufacturing related. And from the R&D perspective, we have technical associates numbering about 2,400, and they're distributed between here in Akron, Ohio, where our headquarters is also, in Luxembourg, and in Hanau, Germany. So we are not only a global production, but also global R&D. We manufacture, as I mentioned, almost any tire that you will see. It's likely to be available as a Goodyear product, with the exception of a bicycle or a lawnmower tire. And within each tire type, you need to realize that there's a broad family covering a wide range of performance envelopes. And those tires have got to deliver a range of attributes. Some of them are listed on the screen there, like comfort and tread wear, traction under wet and icy conditions. And many of those can be in contradiction with each other, presenting a significant development and design challenge. For instance, rolling resistance and tread wear typically work against each other in a modern tire. To develop our products, one of the things we do, like most companies, is we listen to the customer and the consumer, and we take many of our leads then from technology trends in transportation and vehicle development. We are, after all, working in the transportation area. Now, there's a number of areas for technological development affecting tire performance needs, new tire attributes, as well as manufacturing needs. And some of them are listed in this bullet chart here with the arrows. Lighter weight is going to be important to support more efficient cars and tire manufacturing. Intelligence is emerging in so many objects, but it's not excluded from tires. So sensors, telematics, or even road condition monitoring can be envisioned for future tires. Lasting performance is a key consumer demand, and we need to maintain that performance under a range of performance situations for the entire life of the product. Flexibility has become essential in the current manufacturing, along with more efficient manufacturing that can also be modeled and quantified. And all of these directions point to some of the areas illustrated in the red box over on the right, which are technical areas likely to yield appealing opportunities for tire technology and even new business models. And speaking on the business model side, taking a step back before I get into some more specifics, at the enterprise level, we've got broad challenges for innovation that come from the complete value chain, as illustrated there. For the rest of this afternoon, I'm going to talk about product performance and manufacturing, but you'll find that, that the ones that can be found on this chart, for instance, one of the big ones is the use of data for forecasting, informatics, for management of manufacturing complexity, for better forecasting of when to make products. One example for us is that with our supply chains being global, many of our raw materials come from Asia, for example, our lead time is quite significant in terms of ordering to production. So better forecasting will make for better business operations. Going further into Goodyear and the technologies that we're looking for, I think it's useful as a quick backdrop to the developments that we're wanting to achieve for the future. It's useful to look over the history of the pneumatic tire. This is a chart that the company often uses, that even though we'd like to make revolutionary products, the development of the tire since vulcanization was discovered in 1839 by Charles Goodyear has been really evolutionary rather than revolutionary. Goodyear, in fact, was formed almost 60 years after Goodyear found the vulcanization process. But take a note that the basic form of the tires on this chart, whether it's a radial ply or a steel-belted radial or a run-on flat tire, it might appear to be unchanged. But the interior details and the performance attributes have become increasingly more complex and sophisticated to meet the consumer demands. And so much so that a modern passenger tire looks a lot like this when you peel away many of the outer layers. Hopefully many of you have not seen a tire like this if you own it as a consumer on your personal vehicle. But these are many of the components that must work together as an engineered composite. These components are not only designed, but they're formulated and then placed to deliver the correct mechanics, the correct chemistry, and the correct physics for the operation of the tire over thousands of miles for safe, reliable performance, using a large range of different chemical and materials for raw materials. Sometimes up to 60 raw materials can be used in a tire. Another way of looking at that, getting a bit more technical on this chart, is to think about this in terms of the different time scales and the different length scales that play in operating a running tire. Quantum mechanics can inform us about reactive chemistry. We can use molecular dynamics for interface behaviors, and then on to micromechanics and finite element analysis to understand composites and then the whole tire behavior. So looking a little more closely into raw materials, many of these raw materials you recognize, they're drawn from a range of materials that are commodities these days, polymers, fillers. The principal fillers that we use in the modern tire is, of course, carbon black, which is why tires are black, and larger and larger amounts of silica functionalized to work with rubber, curative materials, and then structurally reinforcing materials, steel cords or fiber cords like polyester and nylon, and processing aids to facilitate our manufacturing. About 70% of our materials are petroleum-based. So alternatives to this are a great challenge for us. Now I'm going to spend the remainder of my time talking specifically about some general areas. And what I want to give you here is a raft of challenges that are facing us, and then some more specifics in selected areas. So looking more closely at rubber compounds we typically use, they comprise the following on that chart. And as the earlier chart illustrated, there are different length and time scales at play. For instance, in carbon black, that runs from scales of activity at the tens of nanometers to hundreds of nanometers and then into the micron scale. We've got a lot of reactive solid-state chemistry taking place, and the rheological and mechanical behavior is also complex. Now, many years and decades of development and tuning has produced a highly interactive functional rubber compound that's going to change depending on how it's processed and used. And so based on those observations, what we want to deliver to new products and how we want to improve the current products, I can summarize for you here some of the important technology challenges for tire materials. Now, it's a long list, and I'm going to leave it up there while I just pull out about 4 and give you some verbal background on what we see to be interesting challenges in each of those. And those are the items that are underlined and in italics. So, first one is responsive materials, something that, for instance, might change behavior as a result of some external input, such as water repellency under a wet condition, or mechanical stiffening or softening by some electrical stimulus, or some self-healing mechanism released to arrest crack formation. Second one is tire liners. Most tires use these days about a 0.5 millimeter to 0.75 of a millimeter of a butyl-based polymer to retain the air in a tire, keep it inflated, stop the air diffusing out through the rubber. Now, there are plenty of materials out there with better air barrier properties than butyl that could be used at lower thicknesses for weight reduction. However, there's a lot of significant challenges remaining in terms of the flexing tolerance of those polymers over millions of cycles and at low, maybe as much as minus 40 degrees centigrade, and with sufficient extensibility for manufacturing and service. Thirdly, think about novel cross-linking chemistries. That is, so that we can do reversible cross-linking for reusable rubber. The dyeing rubbers used in tires now, polyisoprene, whether it's natural or synthetic, SBR and PBD, polybutadiene, they're cured by the action of sulfur and sulfur-containing small molecules and accelerator chemicals to introduce a fairly low degree of cross-linking, about 1% by molecular unit. This cross-linking does change with age, flexing, and heat. Furthermore, it's effectively irreversible rather, which poses one of the major barriers to a higher value tire recycling. Lastly is something that's developing recently these days, and that's there's an increased number of circumstances where it's beneficial to attach an object to a tire after manufacture. So we need adhesives for cured tires. So circumstances might be to attach something for decorative purposes, or to attach something functional like a sensor. And the challenge in tire polymers is because of the range of polymer substrates in the tire, butyl, natural rubber, or synthetic, as well as the small molecules and fragments in the tire that can migrate to interfaces and degrade adhesion possibly. So how all these work together, I hope you're beginning to see the theme here is that the behavior interfaces, and so the interface characterization becomes critical. And in the context of rubber tires, we need to better understand the interaction of particles with the rubber, noted here, and the creation of the modified interface that exists around the reinforcing particles within rubber. These are critical challenges for building better tire components. Chain dynamics and interactions at surfaces, for example, friction and wear, are going to help understand tire function on different surfaces. I think the last area that I'm going to talk about in any detail for you to give you further range of challenges is in tire manufacturing. Tire manufacturing is developed into large-scale operations for most tire manufacturing companies that produce tens of thousands of tires a day in a given factory with a layout that looks pretty much like this for pretty much any company. The trouble is, of course, is that transportation has and continues to move towards more flexible and smaller lots. Thus, we need to find ways to effectively manage small lot production in a high volume environment, or devise something entirely new way of producing tires altogether. And in improving our manufacturing efficiency, we can identify some areas of potential benefit. Among those are sensing technologies so that we can more effectively monitor what's going on with our materials as we process them and as they evolve during our manufacturing processing. Complexity is very important as it relates to managing diverse materials, changeovers, process changes, and component mold changes. And lastly, a newly important item for us, the next to the last bullet at the bottom, is we believe that there's value in manufacturing and process modeling, something we see as a counterpart really to the extensive performance modeling that we built in collaboration with Sandia over the last 10 or 20 years. In the area of new products, this is called business model innovation here at Goodyear. This is where we envision entirely new opportunities for tires. And you can see on there some areas I'd like to point your attention to: the idea of stretchable electronics, the idea of self-diagnosing, self-healing composites, and how, for example, do we add services in addition to simply products in the manufacture and operation of tires. I know we're drawing close to the end of our time here, but I've got one summary chart here that I just wanted to let you all take a look at. Some of the things that I've presented and we'll be able to discuss in the follow-up sessions are that our challenges are drawn from business needs, product needs, and manufacturing needs. We are still very, very heavily dependent on material science, and we base that material science dependency on having a fundamental understanding of the physics, chemistry, and mechanics. But that is not all of our opportunities. There are also opportunities in the areas, as you heard from other speakers, in composite science, in electronics, and in big data. Now, we're proud of what we've done in innovation in Goodyear over the years, but to get farther down the road of innovation, we really believe strongly in the open innovation environment as we're practicing here on this webinar with the FLC. And in closing, like many of the others, we've got a follow-up session scheduled now for June 19th. Please get in touch with Michelle if you'd like to have some more discussions with me and other members of my team, and let her know what it is you'd like to talk about. Thank you very much, everybody, for your attention.
Approximately 200 registered for this webinar from virtually all federal agencies. A broad array of industry needs and challenges were highlighted. Collectively, these 5 companies account for over $100 billion in sales and have the capability to bring new technologies to the marketplace. Our expectation is that some of you may have specific questions about these technologies and want to explore collaboration opportunities in more details. As we've said before, if you have questions about what you've heard today, we encourage you to submit them and schedule time to explore matching laboratory capabilities and industry needs. We will display the schedules again on the website, and just as a way of a brief reminder, send any additional questions you may have regarding the presentations to Michelle Chambers. Please answer the survey. Do try to respond by June 14th if you'd like to have a time slot on the June 18 or 19 session, and by June 20th for the June 25 through 27 sessions. I want to have a special thanks for all the presenters. They did an outstanding job. And a thank you for all of you who attended. We look forward to learning about your questions and suggestions for improving this webinar in the future and your participation in the follow-on sessions. Of course, the real test of the merits of this effort will be the long-term results, how much collaboration is really achieved. This concludes the webinar. Thank you again for attending.